Right, I want to show you now how to use the midpoint method. You should already have come across Euler's method. The midpoint method is an improvement on Euler's method, and like Euler's method, it's used to find an approximate solution to differential equations using numerical methods. So if you know a point on a curve and you have a differential equation by which you can calculate the gradient at that point, then you can use the gradient and work in small steps to find approximate y values for x values close to the one you know. It's called the midpoint method because you work with 3 points at a time. The last point is the one you're trying to find. The midpoint is the one whose gradient you use, but you use the gradient at the first point and take 2 steps. Let's have a look at what that means in practice. So here we have a point on a curve, and using a differential equation we can find the gradient at that point. Now usually we wouldn't be able to see the curve, so let's get rid of that. And what we're trying to do is we're going to take steps of 0.1 at a time, so we're going across one big square at a time to find the point on the graph corresponding to an x coordinate of 0.5. So we're starting at 0.1, so that's going to be 4 steps. So for the midpoint method, we work in sets of 3 points, where the third one is the one we're trying to find. But at the moment we've only got 1, so we just use Euler's method to find the second point. So we go along 1 step along that tangent, and there we've got our point B. Let's lose the tangent at A, we don't need that. So what we want to do now is we want to find the point C, we want another step along. And what we're going to do, we're going to use the gradient of the curve at B and then go back to point A and take 2 steps at that gradient. So first of all, we need the gradient at B. There it is. So let's just have a look back at our original curve just to see where we're at. Okay, so point B isn't particularly close to the line, but you can see if the gradient through B, if B was a little bit lower on the curve, then that looks like it would be the gradient. So it looks like we're on safe ground. Okay, let's say goodbye to the curve and move that gradient from B down so it's going through A. Okay, so that's the one we want. We're going to take 2 steps from A now along that gradient and plot our point C. So there we are. C is the x coordinate of 0.3. So we've taken 2 steps. We've got 2 more to go. Let's get rid of that gradient through A. So the 3 points that we're considering now are B, C, and D. These are the ones to find. And we want to use the gradient at C, but going through B and taking 2 steps. So there's our gradient at C. You can see we're looking for a parallel line through B, and so that line is only going to translate upwards a little bit, isn't it? So there we are, the gradient from C going through B. Now we can take 2 steps from B and find point D on that line. Right, 1 more step and we'll have reached our destination. So now the 3 points are C, D, and E. Our midpoint is D, and we want the gradient through D. There we've got it. And then we want that gradient but going through C. We're going to take 2 steps to get E. And there we've got it. We've got an approximation for a point where x is 0.5 on the line. So let's have a look and check how close is that to the curve. That looks pretty good, isn't it? It's quite close, almost on the line. If we look a bit more closely, we zoom in, it's not quite there, is it? But it's a good approximation. So here's the formula that's often used for the midpoint method. So when you look at the formula, you can see there's three different y ordinates referred to. There's the current one, there's the previous one, and there's the next one that we're trying to find. So on the left-hand side of the equation, we start with the next one that we're trying to find, and that is equal to the previous one plus 2 times the step length times the gradient of the current one. Let's have a look at an example using this method.
We're going to use the midpoint method to estimate the y value for a given x value on a function. So take a look at the question. So what we're given is we're given the differential equation and the point on the line, and we're asked to, now note it doesn't actually ask us to use the midpoint method, it just gives us the formula, which might be good or it might not, but either way we're using the midpoint method, and this tells us what we want to find. What's the y value when x is 1.5? Here's our step length. So immediately we can start to fill in the table that I've already drawn underneath. So first our point is given to us, so point 0. We're going to go up in 0.1s, that's our step length, until we get to 1.5. So 5 steps looks like. Okay, so first of all we we need to calculate the gradient at our initial point. So we calculate that using our differential equation. So that's 1 squared take away 2 squared, all divided by 1. So that's going to be -3. Now for the midpoint method, we want to go to find this y value, we want to go back 2 spaces or two rows to find our previous y value, but since we can only go back 1, we use Euler's step-by-step method just to find this one. So we're going to do, so here we're going to use the previous y value plus the step length times the gradient. So that's going to give us 1.7. Now to find the gradient at this point, we can use our differential equation, sub in our values, and that comes out as -1.527. Right, now we can use this midpoint method properly, because to find out this y value, we want to go back to 2 positions to find our y value there, but then we're going to find 2 step lengths using that gradient. So we're going to work out 2 plus 2 steps times the gradient of the previous step. So that gives us a y value of 1.695. Okay, so for at the end of step 2, start step 3, we can find the gradient at this point. So again, sub our values into our differential equation, and we get -1.1929. Right, now we're ready to find our y value here in step 3. So again, we're going to go back, not to the previous one, but the one before, our y value there, and we're going to take 2 steps at that gradient. So it's going to be 1.7 plus 2 steps at that gradient. So that's going to give us a new y value of 1.461. Now we found the x and the y value for this third new point, then we can find out our gradient at this point, x squared minus y squared all over x, and that is going to be minus 0.34. That's 29. Great. Now we can take the double step and go from 2 y values back and take 2 steps at that gradient. So 0.695, 2 steps at the subsequent gradient. And our value here is 1.626. One more double step to take, but before we do, we need to know the gradient at this, what will be the middle point when we're stepping up to our fifth point. So x squared minus y squared all over x gives us a value of minus 0.488. Let's add the fourth decimal place for good measure. Okay, so now we can find, for this value here, we need to go back the 2 spaces for our y value and then take 2 steps at that gradient. So it's 1.461 plus 2 steps at that gradient. And our value is 1.3637. So final answer